In this video lecture, we will go through Heisenberg uncertainty principle. This principle is very important because this principle tells us one of the drawbacks of Bohr's model of atom, which leads to its failure, and it also tells us about the wave mechanical model of atom, which is the future model of atom. So it's important to understand Heisenberg uncertainty principle. And as per Heisenberg uncertainty principle, the position and momentum of microscopic particles, extremely small particles, cannot be measured accurately, right, at the same time, right? We will see the reason why only the position and momentum of microscopic particles cannot be measured accurately as per Heisenberg uncertainty principle. Right, so it states that it is impossible to measure simultaneously both the position and momentum or the velocity of microscopic particle with high accuracy or certainty. So it states that it's impossible to measure position and momentum, or we may also write it as velocity of microscopic particles right simultaneously. With accuracy or certainty, right? Now there is one important thing in Heisenberg uncertainty principle, that Heisenberg uncertainty principle applies only to microscopic particles, that is extremely small particles like electrons. It does not apply to macroscopic particles or the particles or the objects that we see around us. Right, we'll see or we'll look into the reason why it applies to microscopic particles like electrons and not to macroscopic particles. Right, so simply it means it applies to microscopic particles like electrons, and as per Heisenberg uncertainty principle, we cannot determine the position, right, and momentum of small moving microscopic particle accurately or with certainty, right? It applies to moving microscopic particles, small moving microscopic particles, right? So what it means is, if this is this is the structure of atom, say, right, this is your nucleus and this is your orbit, and electron is moving around this orbit, right, which is a microscopic particle. So at any time you cannot go ahead and determine the position of this electron, right, and its velocity, right, at the same time around this atom, right, around this nucleus, I'm sorry. So the position and momentum or velocity of this electron cannot be determined simultaneously with accuracy or with high degree of certainty, right, at any time. Now let's see what is the reason why we cannot determine the position and velocity of microscopic particles, right, like electrons, but we can determine position and velocity of macroscopic particles, right? So when we say we cannot determine the position, right, we say we cannot determine the position and let's say velocity, right, position and velocity. So in order to determine the position of any object, right, we need to view that object. If that object is visible to us, we would be able to locate that object, right? So first thing is the visibility of the object. If you have a light, right, if you shine that object that you want to locate, right, with light, right, then the object will reflect that light, right? And if the light reflected by that object falls in the visible region, By visible region I mean the frequency of the light reflected by the object falls in the visible region of the electromagnetic spectrum, then that object would be visible to us and we would be able to locate that object, right? So the object location or the position, right, is when we can view that object, right? And why we can view this object? We can view this object because the light reflected by the object falls in the visible region, right? We write it as reflected light falls in the visible region of electromagnetic spectrum. We have done electromagnetic spectrum before. It has the arrangement of electromagnetic spectrum is the arrangement of radiations of different wavelength, right? When we arrange radiations of different wavelength or light of different wavelength, right, in an order, then what we get is an electromagnetic spectrum. When we talk about the visible region of electromagnetic spectrum, we mean the region of the electromagnetic spectrum where the wavelength or the frequency of light lies, that we can see, right? Visible region means the frequency or the wavelength of that portion of the spectrum, right, that we can see, right? Those radiations, right, those radiations of the electromagnetic spectrum or the light radiations of the electromagnetic spectrum we can see with our eyes, right? Now if we want to, this is for normal objects, macroscopic, the bigger particles, right? If we want to locate the object, we just shine the object with the light, right, with the visible light that we normally use, the torch light, right? And the light reflected by this object, right, the frequency of the light reflected by the object would also fall in the visible region. Hence we are able to locate the position of that object, right? And what about velocity? We know that light consists of photons, right? And light consists of photons, right? And photons have associated energy given by h nu, right? Now the frequency of light, right, of visible region, right, this, if the photon of light of frequency of visible region will strike the object, right, it will not be able to change the position or the velocity of that moving object. Suppose this is the pen, right? If I'm moving this pen, right, you can easily look this pen, you can locate this pen, right? And the light which is falling on this pen, right, it has photons, right? Because we know that as per the Planck's theory, light consists of photons, right? And photons has associated energy E is equals to h nu. So when the photon will strike this pen, right, so it will transfer some of its energy to this object, but the energy that is transferred is not high enough to change the position or the velocity of this object. So you can accurately at any point of time determine the position and velocity of this object, because the light photons striking this object would not be able to change the position of this object. If this is the position of the object, if suppose this object is lying here, right, and I want to determine the position, I'll shine this, right, the visible light that falls on this, the light that falls on this object, right, would be able to locate this object, because when the photons, right, of light will strike this object, those photons would not be able to change the position or the velocity of this moving object, right? Whatever is the position of this object before light falls on this object, right, will remain same after light falls on it or after the photons of light will strike it, right? So the photons of light or the light would not be able to change the position and momentum of this object, right? When you are trying to locate this object, right, the light that you are using, that light will not change the position or momentum of this object, so you are able to determine the position or momentum of this object simultaneously, right? Now let's talk about microscopic particles, right? Earlier I said that in order to determine the position of an object, we need to view that object, we need to see that object, right? So in order to see some object like this, right, we use ordinary light that we use, right, that falls in the visible region of the electromagnetic spectrum, because this is a bigger object, right? So we can view this object using the normal light that we normally use, right, in our homes. But let's talk about microscopic particles. What about microscopic particles? If you have an atom, right, if you want to see any object at atomic level, right, then the electron moving, right, around the atom would not be visible using the ordinary light, right, because the ordinary light has less frequency, right, and in order to see those extremely small microscopic particles, you need a light of very high frequency, right? So you need, in order to view, right, I'll just mention here, to view microscopic particles, you need light of high frequency, frequency denoted by nu, right? Since the mass of the object of microscopic particles like electrons is very small, right, mass of the microscopic particle is very small. For electron, the mass is 9.1 into 10 to the power of minus 31 kilogram, right, which is very small. Mass of electron is 9.11 into 10 to the power of minus 31 kilogram, which is, we know, small or very small, right? And the mass of bigger particles is high, right? That is why the light that falls on it is not able to change the position or velocity of those objects because of its high mass. Now, microscopic particles, remember, has very small mass, right, and the light that we are using, right, to view those extremely small microscopic particles, the light is of high frequency, right? We are using light of high frequency to view the microscopic particles like electrons, right? So the light that we are using, right, is of high frequency, right? So the photons of light of high frequency would carry high energy as well, right? We know that energy is given by h nu, right? So for microscopic small particles, this nu is high, right? The value of frequency is high, therefore energy of photons is high, right? Now suppose, just imagine an electron that is moving around the nucleus, right? Suppose this is an electron which is moving, right? And let me draw it just a little below. This is an electron which is moving, right? When, in order to view this electron, you use incident light, right, of high frequency, right? So the light, and you are trying to view this electron in this microscope, right? So the light reflected by this electron, due to the light reflected by this electron, you would be able to view this electron in the microscope, right? Light reflected. Now, since I said the energy of this incident light is high, right? Energy of the incident light is high compared to the light that falls in the visible region that we are using in case of bigger particles, macroscopic particles. So when the photon, right, when the photon of high frequency will strike this electron or will collide with this electron in order to locate or view this electron, it will transfer some of its energy to this electron, right? Some of the energy would be transferred to this electron when light of high frequency will collide with the electron. It will transfer some of its energy to the electron, right? It will transfer some of its energy to the electron. So when we are trying to locate this electron, initially it will moving, right, say with the velocity v, right? Now when due to this photon that strikes it, it gains some energy, right? So when it will gain some energy, since the mass of this particle is also very low, this quantity, right, of mass is very, very low. So when light, right, of high frequency will collide with this electron, the position, right, the position of this light the position of this electron and the velocity will get changed, right? Just try to imagine, right, this particle, this microscopic particle is very small, right? So when light of high frequency will fall on it, right, when light of high frequency will fall on it, you would not be able to determine its position or its velocity, right, which was the position and velocity of this electron before the electron, like, collide with this photon, right? What it means is that when light of high frequency, right, will collide with it, it will change its position and it will change its velocity. It will start moving with a high velocity due to the gained electron, due to the gained energy, right, from this photon of light, right? Therefore velocity and hence the momentum of the electron changes, right? On the other hand, say if we use photons of radiation of longer wavelength, we don't use photon, right, of high energy, then what is the case? If we don't use the photon of high frequency, right, or high energy, then we would not be able to locate this electron, this object. Why? Because this object, this is a microscopic particle, we can only view this object when we use a light of high frequency. Since the light is of low frequency, so we would not be able to locate this object. Its velocity would not be changed, right, because of low frequency of light, but at the same time we would not be able to locate this object, right? So if we use photons of radiations having longer wavelength, the velocity and the momentum, right, will not change appreciably, but its position cannot be determined because object will not be visible, right? Therefore light radiations of shorter wavelength are used in order to, or higher frequency would be used in order to locate this object, right? In short, what we mean is to locate electron, light of high frequency would be used, right? And this light of high frequency will change, it will change the velocity and hence the momentum of electron, right? So with whatever velocity this electron was moving before colliding with the photon, right, of high energy, right, that velocity will get changed when the photon of high energy will collide with it. So what it simply means is the energy of this moving electron could not be determined, right, because it gained energy due to this photon and the velocity of the moving electron got changed, right? And let's talk about the other way. When we used light of high frequency, it changed its velocity, right? So velocity could not be determined. We could locate that object, position is determined, but the velocity is not determined. Now since when we used light of high frequency, it changed its velocity, right? Now let's take the other way around. Let's use light of low frequency. Let's use light of low frequency. The light of low frequency would not be able to change the position and momentum of the electron because it has less energy, right? But at the same time, as I said earlier, that in order to view microscopic particles, the extremely small particles, we need a light of high frequency, right? So when you use a light of low frequency or high wavelength denoted by lambda, the particle would not be visible. Particle would not be visible, right? Since the particle is not visible, so you would not be able to locate the particle. Right? Because in order to locate the particle, we need to view the object. Now since I am using light of low frequency, right, or high wavelength, so that its velocity does not get changed, but if the velocity doesn't get changed, at the same time I am not able to view the particle, I am not able to locate the particle because light is of low frequency, and in order to view the microscopic extremely small particles, we need a light of high frequency, right? So this is it, right? Now we are clear why we are able to view the bigger particles without its position and momentum getting changed, right? Whereas the position and momentum of extremely small particles like electron gets changed because on the one hand its mass is very low, right? The mass of extremely small particles is low, and we are using a light of high frequency. When we are using a light of high frequency, it transfers some of its energy to the electron, due to which its velocity changes, right? And at the same time its position also changes, right? Because of the gained velocity, right? So what we are basically doing here is why we cannot find the position and momentum of a microscopic particles, because without disturbing the particle we cannot view this particle, right? So when you disturb a microscopic particle, in a way you are changing its position and momentum. It will change its for sure it will change its velocity, and it may change its velocity also, its position also, right? So in order to view microscopic particles, we need to disturb these particles. that changes its velocity and position, maybe position also. Now there is a mathematical expression, right, for Heisenberg uncertainty principle. If we are talking about position and velocity, the uncertainty is in position and velocity. Let's say the uncertainty, if suppose there is a particle that is moving in x-axis, right, if its position, uncertainty in position along x-axis is delta x in this direction, right, then its uncertainty in velocity would also be measured along x-axis, along same axis, right. So let delta v be its velocity or delta p be its uncertainty in momentum. So the mathematical expression is product of uncertainty in position and uncertainty in momentum, right, is greater than or equal to h upon 4 pi, right. This is a constant. This is the mathematical expression for Heisenberg uncertainty principle, right, which states that the uncertainty in position and uncertainty in momentum is constant, right. The value of the constant is h upon 4 pi, right, and we know that if delta x dot delta p is constant h upon 4 pi, right, then these two quantities are inversely related to one another, right. When we say inversely related to one another, we mean that if delta x is low, right, then delta p is high, right. We can write it like this also, m delta v is equals to h upon 4 pi, or delta x, uncertainty in position, uncertainty in velocity, is equal to h upon 4 pi m, right. So when, like here, when uncertainty in position is high, right, that means when this photon of high energy will strike it, right, in order to locate, we are using light of high frequency, right. So it disturbs its velocity, uncertainty in velocity is high, right. So we are able to locate it due to high frequency, right. So uncertainty in position is less here, right, but uncertainty in velocity is high, right, because this photon of high energy has changed its velocity, right. Here uncertainty in position is low because we are able to locate the object, but at the same time uncertainty in velocity is high because the photon, when collided with the electron, it has changed its velocity. So these two are inversely related to one another, right. Now if we use light of high frequency, high wavelength or low frequency, then it may not change its velocity, right. So this delta v is low, uncertainty in velocity is low, but at the same time we are not able to locate the object. So uncertainty in position is high, we are not able to locate the object, right. Similarly, if we talk about the trajectory of an electron, right, trajectory of the electron has no meaning here. Why? Because as I said, in order to view a microscopic particle, right, we need to disturb the particle, right. So when the particle is disturbed, suppose this is the trajectory followed by a microscopic particle, right, this is the trajectory, here is the electron. When a light of high frequency will strike it, since I said it will disturb it, right, the particle will get disturbed. When I say particle will get disturbed, so earlier it was moving here in this direction, it will get disturbed and it will start moving in this direction. So it will change the trajectory of an electron, the trajectory will get changed, right. So what we say is existence of definite path or trajectory, right. The idea of fixed path or trajectory has been hit hard by uncertainty principle, right. Therefore, it is not possible to talk of trajectory of an electron. You cannot determine the trajectory of an electron, right. The trajectory of this electron cannot be determined because when you view this, in order to view the trajectory, you have to use light of high frequency which will disturb it and change its trajectory path. It has started moving in this direction, so it will change the trajectory of an electron which has no meaning to it, right. That is why in order to determine